Greetings. In this problem, we want to calculate the equilibrium constant. And what we've done is we've mixed together some reactants and products, and we allow the reaction to go to equilibrium, and we measure the concentration of one species at equilibrium. So this would be it's going to be a Rice diagram where we start off writing down the reaction that we're going to investigate. And in this case here, we have NO, 2NO, plus 2H2. And all species are in the gas phase, so I'm going to ignore the phases, plus 2H2O. Okay? And we want to calculate what is K. And K is, at equilibria, the products concentrations to the power of their coefficient. And incidentally, H2O, which is squared, is a gas, so it's part of the K. If it was a liquid or a solid, we would not include it in the K, because that's a heterogeneous equilibria. And then we have the NO squared and the H2 squared. And I'm just writing E here to represent that these are at equilibria. We usually omit the E. It's implicit when you have K that your system is at equilibria. Now, I start with an initial concentrations. If the system's not at equilibria, a reaction occurs. It could go in the forward direction or it could go in the reverse direction. Okay, so change is how much these species have changed as it goes from the initial concentration to the equilibria concentration. And the equilibria concentrations, when put into this expression, give us the value of K. So what did we mix? We have 0.1 moles per liter of NO. We have 0.05 of H2, we have no N2, and we have 0.1 of the vapor phase water, okay? Now this actually represents Q, okay? And I have some condition, and Q is either equal to K, less than or greater than, okay? Since one of these is a 0, we know the reaction must go in this direction, okay? It can't go in that direction because you can't make anything from nothing. And we notice that the 0 is in the numerator, okay, which means Q equals 0, and K must be a positive number, okay? When we have a reactant-loaded system, a reactant-favored system, the denominator is large, so K is a tiny, tiny fraction. But K is always positive, so 0 must be less than K, and reactants become products. We go here, and Q gets larger until it reaches K. Now, to solve this problem, we need the equilibrium concentration of one species, and then we relate how they change in respect to their coefficients as they go from initial to equilibrium. So we were given the equilibrium concentration of the NO, which is 0.062 molar. Okay? So this is what we've been given, and this is a solvable problem. Okay? Now, when I look at the change, I'm asking myself, how far from equilibrium are we? And so every time this reaction moves in this direction, and we know it must move in this direction because we have a 0 there, every time we consume 2 of these, and I'm going to go X, and X is the extent of reaction, we also consume 2 of these, we make 1 of these, and we make 2 of these. Now, initially, we consume a couple, we make some. We consume more, we make more. And at some point, we reach equilibria. And at that point, that's the value of X. So 0.1 minus 2X is saying, how much did I consume as my reaction went from the initial condition to the final condition, which was the equilibrium condition, and now the reaction is over. I also had to consume H2. So I had 0.05 what I started, and I consumed the same amount because the coefficients are the same. while these were being consumed, I produced this at half the rate. So I only made X of this, okay? Because for every 2 of these and 2 of these that I used, I only made 1 of these. But I made this at the same rate, so I made 2x of this, but I already had 0.1 to start with, okay? So these represent the equilibria concentrations. We usually don't write the E down here, but I'm trying to make this clear, and this is what this E is. And what we're saying here is this is my Q. A reaction proceeds, I consume my reactants, I produce my products until the reaction is over, and I have my equilibria distribution. Now, I had to measure one of these, and from that, I could now tell you what the value of X is, okay? So I could say that 0.062 was the amount of this left over after the reaction was over, which is equal to 0.1 minus 2x, what I started with, minus what was consumed, and that gives me a value of X equal 0.019, okay? Now, let's make a couple quick comments here. The maximum amount, X had to be a positive number because I'm consuming this, and the equilibria concentration had to be smaller than the initial concentration, okay? But note, this was actually the limiting reagent, and I couldn't have consumed more of this than existed. So the maximum possible value of X, if this was a one-way arrow, would have been 1/2 0.05 or 0.025. Okay? Because as I'm using this up, I'm also using this up. And what we'll see is that I have 0.062 moles of this left. How much of this do I have left? I have 0.05 minus 2 times 0.019, which is 0.012 moles of this. So note, this is getting consumed up. They're getting consumed at the same rate, but this is a smaller concentration because I started with a smaller concentration. Does that make sense? Okay. And how much of this did I make? I made X of this, which is 0.019. And how much of this did I make? 0.1 plus 2 times X, which would be 0.138. So these represent the equilibrium values. We now put them into the equilibrium expression. So I have 0.019 for my N2. I have 0.138 squared for my H2O. In my denominator, I have a 0.062, which is squared, for my NO. And for the H2, I have 0.012, which is also squared. And this is equal to K equals 653. Okay. And to sum this up, I have initial conditions, and I have one species at equilibrium. Okay. So you had to have things that you mixed and one thing at equilibrium. Then I relate the extensive reactions to the coefficients. Calculate the extent of reaction from the thing that I had a value for at equilibrium. Now, using that value, substitute in, calculate the equilibrium concentrations of the other species, put these into the equilibrium constant expression, solve for K. One other comment, okay? Pretend this was not 0. Pretend this was maybe 0.5, okay? If this was 0.5, this value would be different, okay? And we don't know if the reaction is going to go this way or if it's going to go this way. But if I looked at this, and let's just say that with 0.5, the reaction went this way, then this value would have been bigger than what I started, okay? So if I'm making reactants, okay, the concentration goes up. And when I solve this, so let's just say that this was 0.162. I'm going to use my red marker, okay? when I solve this for x, I get a negative value of x. And what the negative value of x means is that I made reactants and I consumed products, okay? And of course, in this problem, we had a 0 here, okay? And because we had a 0 here, this number had to be less than what I started with, okay? And I did indeed make products, and I consumed reactants. But when you have numerical values up along the entire top, it could go in either direction, okay? And as long as you stick to your math, you'll come up with a proper solution, okay? So there's no reason to say we have to make products. We can easily make reactants. Stick straight true to your math, and you'll come up with the proper equilibrium concentrations. Okay, well, I hope that helps. Good luck.